Everybody, it's 8:30 and I appreciate you're all waking up in the morning, showing up, and all the excitement to hear about magnetic reconnection. It's going to make your day. I'd like to begin by acknowledging my colleagues at two centers. One, the Center for Integrated Computation Analysis of Reconnection and Turbulence. This is a center that I have the privilege to lead. It's a partnership between the University of New Hampshire and Dartmouth College, supported by the Department of Energy. We are also affiliated with the NSF Physics Frontier Center for Magnetic Self-Organization. This is supported by the National Science Foundation. And it's the only plasma physics and plasma astrophysics frontier center that has ever been supported by the NSF. The center is now in its second 5-year cycle, and magnetic reconnection is one of its important themes. So the work that I will talk to you about is actually more of a review of the field, but those that are somewhat more specialized is the outcome of collaboration of a large number of people in these two centers. So yesterday, both in my introductory talk on basic concepts in plasma physics, as well as in the talk on the magnetosphere by Dr. Dorelli, you've heard magnetic reconnection being talked about. I am showing you now, just to pace ourselves, the very beginning of our discussion on this subject. This is a little bit of repetition, but these sort of things can always bear repetition. So what is magnetic reconnection? We begin by first telling you where it does not occur. It does not occur in an ideal plasma, which obeys the ideal MHT Ohm's law. This is the electric field. V is the plasma velocity, B is the magnetic field, C is the speed of light. And if this is equal to 0, and if you're moving in a frame of reference with the plasma, then this will essentially transform itself to a new electric field, E prime, which will be 0 in that frame. So both of these are completely equivalent statements of the ideal MHT Ohm's law. And a consequence of this Ohm's law is in fact Alfvén's theorem, which I talked about yesterday, often stated simply as magnetic field lines are frozen in the plasma and no reconnection occurs as a consequence of that. And in my introductory lecture, I pointed out to you that there are two completely equivalent ways of stating Alfvén's theorem that are mathematically completely equivalent to each other. Each one of them can be derived from the other. The first statement is that if you take a plasma and you take a circuit C1, imagine you paint that with red dye, and you have magnetic field lines threading it. At some initial instant T1, you wait a very short period of time. In fact, as you know, plasma motion being what it is, this circuit element would quickly deform into a contorted pattern relatively quickly. So even these gentle undulations that you see are really the outcome of looking at plasma motion over a very short period of time, but be that as it may, this circuit deforms itself to C2, and you still have magnetic field lines threading it, and Alfvén's theorem simply states in that case that the flux threading C1 is the same as C2, and so it will be for all subsequent times. The circuit being fixed, the circuit being traced out, every point on it according to the equations of plasma motion. This is a statement of magnetic flux conservation. Another alternate statement, referred to often as magnetic field line conservation, is the following. Imagine you draw a magnetic field line in a plasma, and you have plasma elements P1 and P2 sitting on it. You have this field line element convected by plasma motion. It too will deform after a short period of time and subsequently. And Alfvé's theorem then simply says that if P1 and P2 are two elements which are sitting on a plasma at some initial statement, initial instant of time, they'll continue to sit on the same field line for all subsequent times. In other words, like beads on a wire, P1 and P2 are always tied to the same field line, often alternatively stated as saying that plasma elements are tied to the field line or frozen in the fluid. So these are two equivalent ways of stating Alfvé's theorem, and they impose, in fact, powerful topological constraints. Things can deform, but flux remains the same. Plasma elements sitting on the same field line, no matter how deformed the field line gets, would continue to have the same plasma elements sitting on them for all times. This forbids a whole class of motion, the requirements of ideal MHT. But if you should have something on the right-hand side, and I write it in very general form as this function R, with the curl of R being non-zero, this is a rather simplified version of magnetic reconnection. Then, under these circumstances, Alfvé's theorem is violated. That the curl of R is non-zero is significant. For example, if R is eta times J, as you saw me talk about in the ideal MHT equations yesterday and the resistive MHT versions, then of course curl cross eta J is not zero, and that can of course cause reconnection. But if you have the gradient of pressure, a scalar pressure, for example, the curl of that vanishes. So gradient pressure cannot, therefore, cause reconnection by itself. That does not mean it does not have a profound effect on reconnection dynamics. Something else has to break field lines, and I'll get to that in a moment. But the important criterion is that the curl of R should be non-zero. And in a generalized Ohm's law, which we will talk about later in the lecture, for weakly collisional or collisionless plasmas, R contains not only the resistivity, as in the resistive MHT model, which you heard me talk about yesterday, but also includes additional terms, such as the Hall current, electron inertia, and pressure, as I just alluded to. So if you have something on the right-hand side of Ohm's law, okay, and the curl of that is non-zero, you actually set up to have magnetic reconnection. A more precise form of this criterion actually is B dot curl of R not equal to zero, but this is certainly sufficient. So I want to talk about what I mean by topological change. Here is an example that you will often encounter in the laboratory and perhaps also in space plasmas, as observations seem to indicate. Here is a configuration you start out with, magnetic field lines pointing in opposite directions. And I want to emphasize certain things to you, which is that, and this will be also something that will become clearer to you when you do the homework problem. I want to make a distinction between simple resistive diffusion of magnetic field lines and reconnection. What you saw in the previous slide is that if there is an R on the right-hand side of Ohm's law, and if the curl of R is non-zero, it will cause reconnection. But that says nothing about what configuration the magnetic field lines should have. So suppose if you have field lines all pointing in the same direction, like in a conductor, and you let it sit, right? And if there is a finite amount of resistivity, if you sit there long enough, that field line will diffuse away. So the presence of a resistive term on the right-hand side can give you diffusion, right? In what respect is diffusion different from reconnection, if it is? And a critical ingredient that that definition does not address is, in fact, the topology of magnetic field lines. I'm going to make this distinction for the moment, though I'm not going to necessarily say that it's a very hard and fast distinction at all times. There are sometimes situations where diffusion and reconnection become hard to separate. But I think if you do not make an important distinction in the kind of magnetic field configurations where reconnection is possible, you miss something very big about reconnection. So I'm going to say to you then as a tentative conclusion, that you need two things for reconnection to occur. One is having something on the right-hand side of Ohm's law, the curl of which is non-vanishing. The other is that there are preferred configurations of magnetic field lines where such things occur. So here then, I have field lines pointing in opposite directions, and therefore there is an intermediate line, if you think of this as a simple two-dimensional magnetic field where the field line goes to zero. Something very interesting occurs at that point, which is referred to in the literature as the neutral line in magnetic fields. Now, if you impose, so let me tell you my coordinate system. This is x, and this is z, pointing up. And so field lines have this configuration. And imagine you introduce, so this is the configuration, B0 tan hyperbolic z over a pointing in the x direction. And now you impose a sinusoidal perturbation B, okay, varying along x, but pointing in the z direction. And if you superpose these two things, you get this sort of picture. If you draw the new field lines, the null line, where the magnetic field line vanishes, has now been broken up into this cat's eyes or bubble or magnetic island type of structure. This is topological change. You went from a configuration where field lines were pointing exactly in opposite directions, and now you have a new configuration where moving away from the boundaries of these islands, which is called the separatrix. This is called a separatrix because it separates two classes of field lines. Within these field lines, you have field lines close on themselves, right? You see them, right, sitting there, right in the middle, little bubbles. Outside of them, the field lines are going from minus infinity to plus infinity in both directions. So therefore, the separatrix separates two different topological classes of field lines, one going from infinity to infinity, the others closing on themselves. These kinds of changes cannot occur in an ideal plasma. So you will say, well, what happens if I just impose that perturbation? What will go wrong in ideal MHT plasma? You can show rigorously from the ideal MHT equations that ideal MHT equations will never support a perturbation of that form, that in ideal MHT B will always be zero. Work it out. It takes a few pages of algebra. I've done that when I was trying to teach myself the subject. And it's not really something that always the textbooks work out, but it's a very valuable exercise. If you just simply try to put this fluctuation by hand and say, what happens to this little b? That little b is going to go to zero in an ideal plasma. But as soon as you put in a little resistivity, that B can live and can actually give you magnetic island. So when I'm in topological change, I'm in a picture like that. These kinds of structures are actually called magnetic islands, plasmoids, a whole bunch of names that you will hear interchangeably in the laboratory and in the space physics communities. Now, yesterday when Dr. Dorelli was giving you a talk, he referred to the Earth's magnetosphere, and he talked to you about the Dungy model. And he actually was looking at not a simple two-dimensional picture like that, but actually at a three-dimensional picture. And he was pointing out that the simple null point in 3 dimensions is not quite enough, that you really need to have two nulls to define what he called a separator, which separates topologically different classes of field lines. So to put my comments here in perspective with what Dr. Dorelli told you, he too was highlighting for you the importance of topological structures in 3 dimensions. But when you go to 3 dimensions, you have to work at it harder through null-null lines to separate out the topological bundles. And these sorts of magnetic islands can sometimes appear as projections in 2 dimensions of 3-dimensional structures. And I won't go into that today. You saw an example of that talked about. I will actually stay dominantly with a 2-dimensional picture today, even though I don't think 2-dimension is everything, far from it. But it turns out to be a useful place to learn the subject and even to apply it to certain restricted classes of observations. So think of this lecture in a way as more basic, but also sort of complementary to what Dr. Dorelli emphasized yesterday in the context of the Earth's magnetosphere, where analogous concepts will have to be translated in 3 dimensions. With me? Okay? So you understand what topological change means. Why should you study magnetic reconnection? Well, I can give you 2 very important reasons to study it. One is, this process of changing topology often gives you access to states of lower energy by relaxing the magnetic field. In other words, what I'm trying to get at is, you had this state with field lines pointing in opposite directions. And then you had another state where you had these islands form. If you make a simple comparison of the magnetic energy, say, for a zero pressure plasma of the 2 states, you'll find that the magnetic island state has lower energy. So actually, in going from the first state to the second, the plasma is able to give up some magnetic free energy. And because the universe has such an enormous reservoir of energy embedded in magnetic field lines, reconnection is often the way in which you can liberate energy that can be translated into kinetic energy, heat, acceleration of particles, all the spectacular outcomes that you've seen of eruptive events. This is why magnetic reconnection is a subject of great interest. Perhaps even overused. Every time one sees something spectacular happen, one jumps to the conclusion, maybe magnetic reconnection. But I want to point out to you that it is not a panacea for every problem in the universe. And one has to look at whether the circumstances are right for reconnection to occur. In particular, you need 2 things. Dissipation, which is relatively easy to come by in most real plasmas, but also topological configurations. You may have a lot of dissipation, but if the field lines are all pointing in the same direction, they're not going to reconnect, and you can wait for Godot and nothing is going to happen. Okay? So in that case, this is not a concept that can be used very well. But as long as you have these sort of ingredients, it's really a ubiquitous mechanism, including eruptive stellar or solar flares, magnetospheric storms and substorms, and disruptions in fusion plasmas. You'll hear about substorms and storms in Professor Donovan's lecture later today on substorms, which has reconnection, as you will note, as an important possible mechanism that the Themis satellites are actively in the process of studying. There's even a subtler reason to study reconnection, and this is something that is often not sufficiently well emphasized. It is that if you relied on Alfvén's theorem, okay, there's a lot of convective motion that goes on in the universe. Go to accretion disks, stars. So suppose if you take large sectors of magnetic field and imagine them being churned around by convective motions, then field lines can twist and tangle. Ideal MHT does not allow any way for these field lines to get out of that entanglement. You can twist, bend, tie them around. Plasmas are always tied. No pinching off is allowed. No reconnection is allowed. What will be the outcome if there was no reconnection? Due to the complex patterns of convective motion as governed by Alfvén's motion, you will have large-scale magnetic fields tangled up in complicated patterns without any relief. Magnetic reconnection comes and simplifies that pattern, whereby you can actually get large-scale coherent magnetic fields coming about as a result of small-scale reconnection occurring near the regions of entanglement. This is a global process. And therefore, there's a large problem, a large unsolved problem in plasma astrophysics. It's called the dynamo problem. Why is the universe magnetized? Every time I ask this question, think about that question. It sort of gives you a chill up your spine, right? You see magnetic fields everywhere, and why is the universe magnetized despite the fact that there is so much diffusion in the universe? Why haven't all the magnetic fields decayed away? The reason they have not, and so the theorists conjecture, is because the churning of the turbulent motion of the plasma in which these field lines are embedded have a way of recreating or regenerating or sustaining the magnetic field lines that may have been there primordially or not. And this dynamo action, this self-generated dynamo action whereby you self-create or amplify magnetic fields, large-scale motion, not noise, but real large-scale magnetic fields, is in fact relies on reconnection to occur on the small scales, because if it were left to Alfvén's theorem, we would get infinite entanglement and not get the kind of coherent patterns we see. Do you see what I mean? Right? So this is what makes the dynamo problem such a fascinating problem to study, and it's largely an open problem still in plasma astrophysics. We don't understand the sun's magnetic field all that well. We do not understand where the galactic magnetic field comes from, or the interstellar magnetic field, and these are all things that are objects of research. Let me get back to things that we thought we knew. The classical Sweetparker model. And in fact, I'm not going to go through a step-by-step derivation. I submit to you that the basic results of the Sweetparker model, which is a canon of the reconnection literature, can be derived in a few lines by you tonight when I ask you to sketch the steps that led Sweet and Parker to derive their famous scaling law. And we will go through this together tomorrow at the review session, if you haven't all done it already, even if you have done it already. So here is the classic configuration. Remember field lines pointing in opposite directions? And imagine a steady state type of a situation where these field lines are gently driven by a flow represented as UI, driving the field lines together. And as these field lines are squeezed together, the plasma layer is squeezed in between, and fluid is ejected out with an outflow velocity represented by UO or U out, U in, U out. From very simple physical considerations, you can show that the outflow velocity, and you will derive this yourself, is the Alfvén speed, where the Alfvén speed is measured in terms of B by square root of 4 pi rho, the Alfvén speed that you all know about. One can show, as Sweet and Parker did, that in steady state, the inflow velocity is the outflow velocity divided by the Lundquist number raised to the power half. Lundquist number is a dimensionless number which has the following definition: L times the Alfvén speed by eta. If you're doing MKS units, you'll have an additional factor of mu0. I've been a little cavalier about units here. You can restore all of that when you're calculating real numbers. So what this tells you is that in quasi-steady conditions, the speed with which you can bring field lines together and reconnect is in fact a fraction of the Alfvén speed, because this Lundquist number is usually a very large number. For the solar corona, if you use the collisional resistivity, you'll get a number like 10 to the power 14 of the order 10 to the power 15. For the magnetosphere, it's something even ridiculously lower, because it's a very tenuous system. What that tells you is that the reconnection speed, the reconnection rate, is a very small fraction of the Alfvén speed. Now this model was originally designed to actually explain the timescale of flares. And if you rely on this model, this will tell you that flares will take about a few years to happen. That's what it translates itself into if you plug in real numbers. Much too slow to be of real interest. But I want to point out to you one feature though. Notice that the timescale depends on eta to the half, not eta. And in so being, it already is distinguishing itself from diffusion. Diffusion of a magnetic field in a conductor, a highly conducting conductor, scales like eta. In fact, I'll have a little problem for you tonight that you will see this. If you just simply solve the magnetic diffusion equation, magnetic fields decay on a timescale of eta. Reconnection occurs on a timescale of eta to the half. It's already much faster than diffusion. And if you would not have had magnetic field lines pointing in opposite directions but pointing in the same direction, they would diffuse, not reconnect, on the timescale of eta. So Sweetparker is faster than diffusion, significantly. Because for S of the order of 10 to the power 14, S goes like 10 to the power 14, S to the half goes like 10 to the power 7. So Sweetparker diffusion is order of magnitude faster for large values of S than diffusion. Unfortunately, it's not fast enough. And this Sweetparker timescale I want to emphasize to you is a hybrid of the Alfvén timescale and the resistive diffusion timescale, and defined in terms of the Lundquist number. Another way to state S is to think of it as a ratio of the resistive diffusion time divided by the Alfvén time. And for solar flares, it's with 10 to the power 12 and tau waves on a second. This is much too long, as I was saying, a few years. But the key issue here is, what's going on in this reconnection problem? Why are things so slow? And that picture tells you the story. That picture tells you that field lines are coming together and reconnecting over an extended scale, which is much longer than it is wide. And these were what were called the Y points of Sarovatsky, who actually made really important contributions to reconnection theory at a mathematical level, though not appreciated as such until much later. And so I would refer to them as Sarovatsky Y points. And an important issue is, why is Sweetparker reconnection so slow? So if you simply do incompressible plasma, imagine the plasma coming out. V in times L is the amount of fluid coming in. V out times delta is the amount of fluid going out. If V out equals VA, as he will demonstrate, then V in is delta over L. And it is this. That's a very small number. Look back to the previous picture. This is delta. This is L. That's what is killing Sweetparker reconnection, the ratio of the two. Okay? Petschek essentially grasped this very important point. And based on intuition and his ideas from hydrodynamic shock theory, he argued that the reason why Sweetparker is so slow is because the reconnection layer is much longer than it is wide. So think of a geometric configuration where the length and the width are about similar. And he argued that you could drive the system with boundary conditions such that, crafting things boundary, nature is always inventive, so nature will find her own boundary conditions, to in fact realize a reconnection layer in which the length and width are comparable. And this is in fact what is called more classical X-point type configuration. If you should contrast that with the Sarovatsky Y-point type of configuration, much longer than it is wide, you begin to see that Petschek actually grasped a very, very important geometric notion that has persisted in the literature even as we have transcended Petschek, as I will go and talk to you about later today. But then he actually gave a simple heuristic theory, and he argued that the reconnection wouldn't go as slow as Sweetparker, that it would actually go as the Alfvén timescale times the log of the Lundquist number, which is a lot more favorable than being divided by s to the half, which is what you had in the Sweetparker model. Well, if you plug in the numbers for the solar corona, you will get numbers like 100 seconds, which is why when he proposed this model, you heard Dr. Dorelli give you this quotation from Dr. Sweet when Dr. Petschek first presented his model, that you have the right idea and you have solved this problem that Parker and I have been struggling with for years, and I rather like your model. And so then back in 1962, it was assumed that the reconnection problem was solved. The flare problem was solved. The main thing you needed to do was to drive your reconnection geometry to this X-point-like structure with appropriate boundary conditions, and you're in business. This persisted until rumblings were heard by people who tried to obtain, using computer codes, the Sweetparker and Petschek-like solutions. And there's a long history of these papers. You see this beginning Satoshi Hayashi in 1979, Ugai 84, and a whole sequence of papers since that time. But the paper that made the greatest difference was this paper of Biscamp, 1986. He should be given credit for having done some superb computational work. And this is what a really learning thing for students to realize is the best physics gets done, the best nonlinear physics gets done, is when you complement mathematical analysis with good computational or numerical experiments, where you can test out that the approximations that you make in your analysis are in fact supported by computational solutions. And that's what Biscamp did. As computers became more able, he was able to actually test whether one could actually get patch check. And what emerged is the following, that the patch check model is not realizable in high Lundquist number plasmas for which it is designed, unless the resistivity is locally enhanced by hand or by plasma physics at the X point itself. In other words, if you give a very large Lundquist number to the system and let it go, you're not going to get this result unless you also insist that you will go at the X point as your computer code is running or as your experiment is going on, but something happens that locally enhances the resistivity locally to a very large value, even though it's very large, very small, far away from the X point. It's called localized resistivity, took the name anomalous resistivity, and to this day, global MHT codes, which have trouble resolving very thin current layers, make diffusion matter by going and enhancing resistivity locally when the current density becomes too unmanageable. At that particular point, you're really using computer expediency to control your code behavior. Whether nature really does that or not is an open question. I'm not saying that this cannot happen. I'm just saying that you have to miraculously produce resistivity at the X point to get patch check. Okay? Now, what if you don't do that? In the absence of such anomalous enhancement, the reconnection layer evolves dynamically to form Y points and realize a Sweetparker regime. Here is one that was done in my own theory group many, many years ago. There are an n number of pictures like these, thousands. I just chose this because it happened to be one that I have a slide for. Is that imagine you're trying to simulate solar coronal activity. And a typical popular model is you set up a two-dimensional vacuum field with field lines pointing. And the reason why this is an interesting state is that it is pre-biased to have an X point. So if any place patch check would stay at the X point, this would be it, right? Well, now go and induce reconnection in this system, and you can induce reconnection even in this vacuum system initially by moving these foot points as nature tends to do in the photosphere. When you do that, the system deviates away from the vacuum field, current density builds up, but within about 30 alphane time scales, look what's happening. The X point is becoming like an extended Y point, strongly reminiscent of Sweetparker. So even though you pre-bias the system to an initial X point, what you did realize were the extended Y points of Sarovatsky. What kind of reconnection are you getting in this system? The Sweetparker rate. Nothing that goes as tau A times log S by tau 8 by S3/2. Patch check theory is dead unless you enhance resistivity locally at the X point. Okay? So, that was one feature. Other things, people started thinking about these sorts of reconnection things, and are steady-state models really adequate to describe reconnection events in nature, which are often impulsive? Along with that came what is called the onset or trigger problem. Remember, the Sweetparker model, as you will see when you do the homework problem tonight, assumes that del t is 0. No time dependence in the problem. But what happens in most systems? What happens in most systems is that the dynamics exhibits an impulsiveness, that is a sudden change in the time derivative of the reconnection rate. Let me explain. What really happens is that the magnetic configuration evolves slowly for a long period of time, only to undergo a sudden dynamical change over a much shorter period of time. Think of a substorm. Think of a solar flare. Just before, everything is quiet, bang, it goes, right? Something suddenly changes. This is not the quasi-steady behavior prior to the onset. At onset itself goes through very rapid change. So if reconnection is the underlying mechanism, the burden is on reconnection theories to account not just for one time scale, but for this time history of slow evolution and then sudden change. This is a powerful constraint on theories, which has become more and more precise as observations have become more and more precise. And certainly in laboratory plasma studies, the lack of impulsiveness in many models has been enough to rule them out. And so the tokamak literature, for example, is full of those kinds of problems. I won't go into that today. This is a heliophysics summer school. But it suffices to know that if you solve the onset problem in one field, remember you're solving the onset problem in more than one field. And the exact reason may not be the same, the parameters may not be the same, and the boundary conditions may not be the same. Those are important details that may vary from context to context. But the onset problem is a fundamental problem in a whole lot of situations, and I'm going to illustrate that by drawing an example that Professor Donovan also is going to draw on substorms, and later you'll also hear from Professors Dr. Shriver and Dr. Judge about importance in solar flares and other such eruptive activity. I want to tell you that in many of these cases, when people simulate them, they see current densities rising to very large values. You saw that when I was drawing that little picture with the little X point. You saw that thin red region. If you examine the current density there, that's extremely large. And one of the great challenges of computer codes is in fact to run in the high Lundquist number regime, where the current densities can be very intense. And this is precisely the reason why global codes have trouble with them, because they have to do very large scales, and they also do the small scales, and it's extremely hard to do justice to both. This is not just an issue of cleverness. It's a question of what is even computationally feasible. And people are getting better and better at it. I should tell you, yesterday when I told you that a peak magnetosphere is still not possible, I had a student come up to me and say later on, and I was rather happy to hear this, "It's happening in my group." That's great. Yes, I do agree that peak magnetospheres may happen over the next 5 years. I may have overstated the case somewhat. But generally speaking, computational issues are pretty challenging. And you can't really solve all these problems in large dimensions all the time using all the physics you like because of phenomena like this where you have singular structures. Well, now let me go to the magnetospheric substorm and try to begin with a cartoon, and Professor Donovan will give you more details on this. It typically happens, not always, but typically happens with the solar wind magnetic field turning southward. Then it reconnects with the magnetic field, the dipole field pointing in the opposite directions. Flux gets transferred from the so-called day side, the sun being here, to the night side, with a thinning of the plasma sheet and production of a local X point. This is a cartoon, which often is observationally seen to be at distances of about 25 to 30 Earth radii away from the Earth. And if you are monitoring what is going on in the aurora, and these are some beautiful, spectacular pictures taken by John Sigworth, who passed away rather young, unfortunately for all of us, and Professor Lou Frank of the University of Iowa. And what you see here is how the substorm manifests itself. So what happens is that thinning down occurs in the magnetotail, ostensibly reconnection occurs at those distances, and a lot of further dynamics happens, which is exactly why the substorm problem is so interesting, that you will hear about from Professor Donovan. But eventual manifestation of all that substorm dynamics is that you see an auroral bulge. A sudden intense bulge in the auroral ovals is the start of what is an auroral substorm, and it forms close to the midnight sector and moves rapidly poleward. And you will see this movement occurring in these pictures. You see that? This broadening, this is the classic substorm picture, is a sudden brightening. So what you have to explain, if you think reconnection is the picture, is why is it that things were quiescent and then things suddenly took off? The impulsive signature that I'm talking about. And I claim again, I'm making this point for emphasis. It's not enough just to say, something will happen and bang, I get reconnection. But why did nature wait so long before it actually reconnected? What was happening in the growth phase of the substorm? Does the same theory, which gives you the impulsiveness, also give you the slow growth phase? And I claim that if you are a theorist who is pushing himself hard enough, you will use these timescales as determining for you whether your theory is sufficiently good or not. And one of the things that has happened in the field is that even before the arrival of multi-satellite missions like Cluster, Themis, MMS, people were quite ingenious about trying to figure out what is going on. This is a picture from Otani, and it's a contested picture, I should tell you now, because we're learning a lot and a lot more. But nonetheless, it's a very interesting picture, one that many people still argue is going on at distances of about 10 Earth radii. I told you that an X point is formed somewhere between 25 and 35 Earth radii, or maybe even a little closer, 20 Earth radii or so. Largely, Geotail and other satellites have put to rest at least that particular issue, that you do form that. But the question is that what is the onset of an auroral substorm? There is major disagreement on this point. And what one conjecture is, in fact, it's known as the Kiruna conjecture, but it is now more than a conjecture, is that the most interesting activity actually occurs not at 25 to 30 Earth radii, but much closer in, near the Earth, a distance of about 10 Earth radii or so. And Otani gave this picture of the current density changing at a distance of about, I think his observations were made precisely at about 8.8 RE, where the cross-tail current density, now you're looking at the plane of the cross-tail current density as emerging out of the plane of the paper in the two-dimensional cartoon. And what Otani said was that there were 3 timescales. A growth phase lasting 30 to 45 minutes, an impulsive growth phase that lasts less than a minute, and then a current disruption phase that lasts about 10 seconds. 3 timescales. At what point in this process would you say the plasma is steady state? Question for you. I'm getting you out of any possible slumber you may be heading off to early in the morning. When is the plasma in steady state in this picture? Come on, guys. Did I hear an answer? Yes? It's not, exactly. One point, maybe the inflection point, the maximum where the derivative is just transiently 0, right? Where else is the derivative 0? Nowhere at all. So what use is it to rely on steady state models to explain a multiplicity of timescales? 0. Well, some insight. We have to begin somewhere, which is why steady state is a good place to start, but it's not enough to finish there. So let's not get too carried away with steady state models. Keep that in mind. What about solar flares? You'll see a lot more beautiful pictures, but looking at white light, people are figuring out what electric fields look like. And this is a log plot of the same thing, a slow phase, sudden, and a decay. Complicated timescales, right? But these are measured. And somebody asked me yesterday at the end of my first lecture, can you give us places where MHT breaks down, that we know MHT breaks down? This is a place where we need to be careful about. Why? Because if you look at the measured side of the electric field, they're very large. They're much larger than the Dreiser field. The Dreiser field in these plasmas is the critical electric field over which electrons can never be slowed down enough by collisions with other particles. They run away. These are all runaway fields. What happens when electrons run away, where electric fields are accelerating ever to higher and higher energies? Even if you start out with a Maxwellian, you're going to create long tails out of them. Those tails are going to then violate the premise of the MHT theory, which is really true for near Maxwellian distribution functions. So the observations are telling you that if MHT is working, it's for reasons that are rather miraculous in these sorts of situations, because electric fields are much too large. Okay? This is not a theorist's dream. It's a theorist's dream because the problem is hard. But it's not something that we manufacture. These are measured electric fields. So what people concluded from this, that really resistive MHT with Petschek dead with Sweetparker being the only game in town, is not going to lead us anywhere. So over the last 15 to 20 years or so, people have moved away from resistive MHT models. And I'll tell you by the end of this talk why, perversely, we are coming back again to the MHT model to still learn new things. But let me move on from here. What people argued, in fact, is that if you look at textbook example, this is a generalized Ohm's law. And this is a slide I took from Professor Longcope's lecture on magnetic reconnection 2 summer schools ago. And what you see here is E equals minus VI cross B. Your MHT equations actually had E plus V cross B. V is essentially V ion, because in a single fluid, the ion mass controls what the mass convection velocity is, and eta J. These are the only terms you had. All these terms you see, 2, 3, and 4, are what are generalized Ohm's law terms. Okay, so when are they important? You can make estimates. If you compare 1 with 5, it goes like L V mu 0 by eta. That's what we call the magnetic Reynolds number. I'm not calling it the Lundquist number for a special reason. It's because the way it is defined with this little subscript L, which is a characteristic length, which I'm not calling the system length. If you should replace that L by the large L of the system, it'll become the Lundquist number. But just nomenclature-wise, that's in fact the magnetic Reynolds number. If you take 1 over 2 and take the ratio, you will find that that's L over C over omega PE squared. C over omega PE is the electron skin depth. If you take the ratio of 1 over 4, you will find that that scales over L over C over omega PI, the ion skin depth. So this, in fact, is term 4, the so-called Hall current term. Okay? And 1 over 3 is V over Cs L over rho I. This is roughly how the pressure term scales. Now, if the pressure is actually a scalar, and if the density is a constant, even though it's an important term on the right-hand side of Ohm's law, the curl of that is going to be 0. Remember I told you that? So if the pressure is a scalar and density is a constant, the gradient pressure term cannot break Ohm's, cannot give you reconnection. You need something else. And in collisionless plasmas is often the electron inertia, which comes in, the curl of which is non-zero and takes the play role. That is not to say that the pressure term is unimportant. I repeat that. Just because its curl is 0 doesn't mean it's unimportant for the whole problem. It isn't. If pressure is a tensor, though, which is often the case, then curl of del dot P is non-zero, then pressure can break field lines. This is what happens in kinetic plasmas. In PIC codes, for example, where pressure is usually a tensor, or in collisionless kinetic plasmas, where we can actually break field lines. So what you're getting from this, then, is a relative is a sense of the relative magnitudes of the various terms. And so clearly then, whether a term matters or not depends very much on what scales you are looking at. Okay? If the scales that you're looking at are much larger than the ion skin depth or the electron skin depth, then these terms don't matter. That is what will happen on the global scales. Okay? But then if you shrink down to these current layers, the reconnection layers, where the characteristic scale length is of the order of the ion skin depth or the electron skin depth, then you have to retain these terms. What are we looking at then? We're looking at then what I called was this singular perturbation problem. Very far out, E plus V cross B equals 0 is a very good approximation. As you come closer in, if it is a resistivity, it has J in it, remember? J is not very large far away, but J gets very large in that singular layer, as you saw in the simulation. So eta may be small, but J may be very large. The two may be combining to give you a term that is comparable to other terms in the equation. Over what range does that happen? Over the length, over the width of the current layer. And there, the order of the differential equation goes up. You're solving a boundary layer problem by asymptotic analysis or on the computer, you have to be very careful. Because if you throw it away everywhere, you'll be in error. Right? So what you're looking at now is a reconnection problem where you have outer region in the language of mathematics, where E plus V cross B equals 0 is often very good. And then when you get to these narrow layers, resistivity, electron inertia, Hall current, pressure gradient become very important. Now, if you're dealing with very collision-less plasmas, that term is very small. And it is overwhelmed by these other more collision-less contributions, hence the whole field of collision-less reconnection that is controlled by Hall current, pressure gradient, and so on and so forth. So, just to emphasize, on large-scale plasma is an ideal conductor, and Professor Longcope rightly puts us on guard, the good physicist that he is, that when you get into regions of very small b, beware. Because when b gets very small, the Lama radii of particle get very, very large. You have the violation of MHT at another level. But unless the field is terribly weak, it's okay to do a model where you have a large scale ideal MHT, small scale do better. Okay? So, written in terms of dimensionless variables, that ideal MHT Ohm's law, we are now going to get to a model which I call Hall magnetohydrodynamics, which makes the simplifying approximation that the pressure tensor term that you saw written in the previous slide is actually a scalar. So replace del dot P tensor by grad P. And then if you write things in dimensionless form, what you will find is E plus V cross B on the left-hand side, 1 over S, that's the resistive diffusion term that you know about. This is the electron inertia term, dE squared, which scales like system size divided by C over omega PE. Di over N, Di is the ion skin depth, and beta is the plasma beta, electron beta. Now remember, I make this big challenge to you about the impulsive problem, right? Will this model answer that? We all berated Sweetparker because the time scale wasn't right and there was no impulsiveness. But can we get a faster time scale and impulsiveness out of the Hall MHT model? Okay? So many years ago, some of us wrote down a simple criterion. It is that the following. Suppose if you start out with a broad current layer, and the layer goes through reconnection, it gradually thins down, and this actually happens during magnetotail substorms, and then the thickness of the current layer falls below the ion skin depth, so that the Sweetparker width, okay, really, to be very precise, falls below the ion skin depth. As soon as that happens, we argued that these terms would become very important, and the system would go through a rapid impulsive transition to a much higher reconnection rate. Do you get me? Let me repeat. You start out with a broad current layer, and you're reconnecting. First, if you have some resistivity, it's going like Sweetparker, which is quite slow. Then the current layer gradually starts thinning down. And the thin current sheet, the Sweetparker layer, is also thinning down along with the broad current layer. As soon as that falls below the ion skin depth, these terms are going to become important, and they're going to give you a much higher reconnection rate. To illustrate this picture, so I'm going to put this in words. As the original current sheet thins down, it will inevitably reach kinetic scales described by a generalized Ohm's law, including Hall current and electron pressure gradient. A criterion has emerged from Hall MHT and has been tested carefully in laboratory experiments. This criterion, which was developed by a number of us, the Sweetparker width falling below the ion skin depth, and actually another person who contributed greatly to this, and you'll see this in the following slide, is also John Dorelli himself. And so this criterion was tested out. And so I want to show you, and here we cite his work as well, is that here you have reverse magnetic fields, and imagine you're inducing reconnection by imposing flows. So I'm going to show you a computer run. One is pure resistive MHT, high Lundquist number MHT. Another with the same initial conditions, you have the Hall terms turned on. What happens in resistive MHT is that you get extended current sheets, thin, long. The electric field, perpendicular to the plane of the paper, is on the same scale. This is just, EZ is just eta times JZ. Eta is a constant, so they're identical profiles. Are you with me? Right? And these are the Sweetparker jets, the outflow things going out and alphane speed outside. This is reconnection occurring on the resistive timescales, exactly according to the prediction of the Sweetparker model. Now, do the same simulation, turn on the Hall terms. What will happen is, you'll see this feature transiently for a short period of time, and then you will see this. A dramatic readjustment in the nature of the current layer itself. To this day, and this is a really great problem for all of you, we do not have a very, very good theory, just very heuristic arguments for why the current layer behaves in this manner. What does it do? Well, it collapses from its extended current sheet to this X-point type structure. Remember the kind that Petschek had imagined? So that you can somehow get that large current sheet shrunk down, you would enhance the reconnection rate. Well, that's exactly what is happening, except you don't need any anomalous resistivity. The system is doing this on its own due to the intervention of the Hall current, where the current layer has fallen below the ion skin depth. Furthermore, notice that EZ is not just a simple constant multiplicative profile from JZ. EZ has a layer width which is actually much broader than the localization of the current density. There's a scale separation that is actually occurring. The current is mostly carried by electrons in this current density. This width is controlled by the ions. So Hall MHT is a place where we're abandoning the usual picture of electrons and ions moving together as they do in an MHT. Here electrons and ions move together only in the large ideal MHT region, but then as they come closer and closer to the reconnection layer, at a width of about ion skin depth, the ions take off in different directions. Then you go further in, the electrons keep going because they're still frozen in to the plasma, and they actually go and support the current layer. And the jets now look very Petschek-like, opening up widely. And in fact, your intuition on this, now the reconnection rate should be enhanced because I've gone from Y points to X points, is exactly correct. Because if you calculate the rate at which flux is chewed up, this is the dotted curve for Hall. This is a log plot, remember. And guess what? It's showing an impulsive enhancement. So is the current density. Therefore, Hall models are beginning to show now simultaneously two things that we were looking for as impulsive signatures. A slow phase, when things are going Sweetparker-like, but then a sudden transition to a much more rapid reconnection rate brought about due to the presence of the Hall current and pressure gradient terms. Okay? This picture has now been tested not just by fluid models, but by particle and cell simulations as well, and so on and so forth. But this is another picture I took out of Professor Drake's webpage. And why I wanted to show you this is because he shows the electron flows. And you see them penetrating all the way in, and the ions actually decouple. The ion current density is broader than the electron current density. You see a clear scale separation happening between ion and electron dynamics in the reconnection layer itself. So the reconnection layer is becoming a very interesting place. And this is what Dr. Dorelli was referring to yesterday, why the MMS mission was actually designed. In fact, the MMS mission is designed to focus on this so-called electron diffusion region problem. And the dynamics is quite impulsive. The structures are very localized, which is why MMS has to operate in this burst mode, getting as much data as it can in short period of time, and the requirements of telemetry don't allow it to continue to be in that burst mode forever because you can't really radio down all this information equally fast. But this is the object of focus of MMS, the electron diffusion region. And in a way, that mission was stimulated by theoretical discoveries of the last 15 to 20 years, roughly, moving away from the classical Sweetparker model. The laboratory people have not been idle, neither been ideal nor idle. And this is the Princeton MRX experiment, known as the magnetic reconnection experiment, where they actually tested out that criterion I told you with great care, for which they were actually one of the reasons why they were awarded the Dawson Award for Excellence in Plasma Physics for carrying out reconnection layer studies. This was a little after their careful vindication of the Sweetparker model. This is a modest side experiments, a laboratory experiments, where they controlled the plasma density, the filling pressure. So by controlling the plasma density, they can either be in the collisional or the collisionless regime. And they can measure the reconnection electric field In the collisional regime, they get Sweetparker. And they did a marvelous job of testing out Sweetparker model. And then as you drop the density, you see this X-point type structure happening. And if you look at these scales, these electric fields are a lot higher. And so they were pointing out that as they're heading in the collisionless regime, they have this onset criterion. So the problem of fast reconnection and sudden onset could be said to be solved by these studies. That did not mean everything was understood. Far from it. Substorms or flares pose challenging mysteries. But at least so far, so good. The story doesn't end. I'm going to go on. But I should tell you that this criterion is actually a fairly broad applicability. Here, Masaki Yamada of the Princeton Plasma Physics Laboratory wrote that criteria in terms of the lambda mean free path of the system and the system size. And you can see, roughly speaking, that this criterion is going to be obeyed better and better as the lambda mean free path gets larger and larger. When that happens, you're having less and less frequent collisions in the system, and the system is getting more and more collision-less. Here is a listing of MRX, tokamaks, magnetosphere, solar flare, the interstellar medium, protostar. In almost all cases, except the interstellar medium, this criterion is obeyed remarkably well. And so it can produce a plausible criterion for sudden onset in a number of contexts. This is just to make that broader point. When it comes to the substorm itself, we simulated using the Earth's dipole field, and this will be again the subject of Professor Donovan's talk later. You get pinning down of the current sheet, and how well does a Hall MHT model do? Well, here is Otani's original picture. You get a very slow growth phase, an enhancement, and a disruption. But what happens in our picture, these were essentially 2D or 2.5D simulations where we were not allowing any variation in the plane perpendicular to the paper. We do quite well in the slow growth phase and this impulsive onset phase. But in this model, we do poorly in terms of explaining this sudden relaxation. It's about 10 seconds, this current disruption. Our model is more like, 5 to 6 minutes. Much too long. And therefore, we did not solve the sudden disruption problem by actually doing this. And the speculation is that three-dimensional instabilities, pressure-driven instabilities of the ballooning type or others, are ones that are hastening the process. Remains to be seen. We've even done nonlinear ballooning studies. Not quite enough. We need to couple in the currents. The story goes on. One of the great things about the substorm problem that is clear to me that it's going to stretch it to its utmost before it yields itself. And it will happen because of a confluence of great observations and great simulations and theory. Still getting there. Problem for many of you to work on. Okay? Themis is going to explore this. These are slides that you've seen before, so I won't dwell on them. This is the magnetosphere multiscale mission referred to as MMS. 4 satellites that will actually solve the magnetospheric acceleration, reconnection, and turbulence problem. I always like it when missions proclaim the goals that they will meet. We will solve the reconnection problem. One of my friends in the fusion community said, if we ever advertised a tokamak saying that we're going to solve the reconnection problem, it will be dead on arrival. One of the marvelous things about NASA missions is that it still states as its objective as a physics problem that it wants to solve. And people give you millions and billions of dollars to build the thing and solve the problem. Except it's also one of the ironies of NASA that after the mission is flown, there is no more money to analyze anything. So we get all this data, reams and reams of data, but not really to solve the problem. But be that as it may, that's my quibble, as many people's quibbles are with NASA. But it is great that you can open up the MMS webpage or the Solar Pro Plus webpage and you can say, we're going to solve the coronal heating problem. Yay! What more can we need as a mission in life, Unencumbered by delivery of anything really practical, just understand things. Well, this is MMS mission again. And to just show the commonality of, and I really believe in this, solar coronal people have given us absolutely gorgeous images. They've given us terribly resolved current layers. Magnetospheric physics people have given us in situ measurements that have done very poorly with imaging. And this is not their fault. The parameter regimes are such as to not enable both happening at the same time, though things are changing. So, but the point that we are trying to make here, that what may be going on in the magnetotail may also be going on in solar flare slides. Just because we can't quite resolve current layers in solar flares doesn't mean that these effects are unimportant. In fact, if you calculate that number, di over delta sp, that I told you about for the solar corona, you will find that it is quite unimportant in the chromosphere. In other words, delta sp is often larger than di in the chromosphere. But if you go up to the middle corona, it becomes comparable and even smaller. So it's not clear to me at all that these effects are not important in the corona, even though they have not been seen to be such. But in the magnetosphere, they've actually probed, when we have gotten lucky, these diffusion regions. Cluster has given us tremendous amount of evidence in support of this. But you know that such effects have actually been seen. And this is, in fact, from a Scientific American article of Birch and Drake. The point is being made that the same physics is operative in the magnetotail as well as in the sun. And maybe even coronal mass ejections, spectacular things. The Earth is this blue dot sitting there compared with the size of this. And that reconnection can underlie coronal mass ejections is something that is very much talked about. In all of these cases, you will note that reconnection is often not the whole picture. Like I talked about in the magnetotail, right? Our attempts at trying to simulate it, we got 2 timescales right and the 3rd timescale wrong. And we were speculating that the 3rd timescale may be due to an ideal instability, which has got nothing to do. It's the interchange or ballooning instability that I referred to in my talk, nothing to do with reconnection. So reconnection can be a great facilitator. It can take you often a large part of the way there. It can even be a final sequel to a lot of interesting dynamics that are happening on the ideal time scale that we need to study. So don't be blinded by the success of reconnection models. There are other things in life that makes it more interesting and in fact makes it closer in observations in some context. So I'm not suggesting by this simple cartoon that CMEs can be completely understood by reconnection. There are a large number of people who feel that is an interplay of reconnection and ideal instabilities that actually drives these systems. Now I want to tell you about something that is relatively recent, but extremely interesting. I told you the Sweetparker model was dead, right? I've come to regret that statement, written in some of my own papers, and with some joy because we discovered new things. The Sweetparker model is almost like the Kolmogorov turbulence model. You know, it's like an icon of the literature. You can derive it in 5 lines, as you will tonight. I keep warning you. And it has stood the test of time, right? Simulations, theory, nobody challenged anything. Until recently. And what did we learn? What has happened is that one of the things that Sweetparker relied on was a stable Sadovatsky type of current sheet. You get this guy, you know, long, thin, sits there, gets in your way, doesn't give you a fast enough reconnection. What we have learned in the last 3 years is that this is not the whole story. That when the Lundquist number exceeds a certain critical number, turns out to be 10,000. Why, don't ask me, I don't have a precise estimate of that, but heuristic arguments why that is 10,000. That this current sheet is not stable, and that is the flaw of Sweetparker model. Sweetparker doesn't sit there for large systems. Remember, S goes like L VA over eta? So you fix eta, fix the alpha in speed, but make the system larger and larger. You're going to get a Lundquist number exceed a certain threshold. What happens then is the system becomes violently unstable to a secondary reconnecting instability, which I have called the plasmoid instability, and that has stuck in the literature. And the first correct analysis was actually done by a graduate student. It was in his PhD thesis. He actually did the linear stability analysis of thin current sheets and pinned down what this growth rate is. What he found was that there is a nearly super alphenic reconnecting instability that breaks up this current sheet. But then in his thesis, he couldn't explore what happens nonlinearly because he was running a simulation, but he saw this instability, but it produced a huge island and sat in the middle, and the reconnection rate showed a short rise but died very quickly. So he wasn't sure really that this has major nonlinear consequences. And I looked at his thesis. First, I had total disbelief that we had been dunces, that we hadn't realized that there was this rapid instability. But then I also thought this must have important nonlinear consequences. And in our group, we developed this picture further, and this is now, I think, fairly widely accepted. So I want to tell you, though, the fact that you can have secondary reconnecting instabilities called tearing instabilities of highest current sheets has been known for some time. If you look at books, you will see it. What was not made precise is what the growth rate of the secondary instability is. How rapid is it? What are its nonlinear consequences? So you find papers, no question. You even find people who did turbulent simulations where you see coherent structures swimming in a turbulent sea, done by people like Mathis and Lumpkin and other people. But they didn't talk about the pivotal role played by this plasmoid instability. And over the last 4 years, 2008 onwards, is where we're now beginning to explore what the consequences are. And I want to show you this with a simulation that we have set up. Here is a long, thin Sweetparker current sheet. And what we did was that we put in a little noise source on the right-hand side. This was something that Loureiro didn't do. What this noise source does is like a white noise source. See, MHT codes, unlike particle and cell codes, are very noiseless. They don't break symmetry very easily. But if you impose a little noise, they don't play a very important role in the dynamics. They just break the symmetry of the code and enable you certain interesting dynamics, which you will now see play out in the next movie. Where is this thing now? Okay. See what happening to the current sheet. Now this is pure resistive MHT, okay? No Hall currents, no pressure gradients, nothing. Thins down, things start forming, these islands. And see how the current sheet gets thinner and thinner. You get more and more of a cascading effect, if you will. More and more of these islands emerging. And the system continues to be violently unstable in this mode. And if you continue this simulation even further, okay, that X point would stretch again, would break up again into plasmoids. So it goes through a repeated sequence like that. And if you calculate the reconnection rate, what you will find is that it obeys the Sweetparker rate till about 10,000 and then becomes flat in its dependence with respect to the Lundquist number. Sweetparker is going along this road, and this has already now reached this value. This number is like 0.01 VA, and it's independent of the Lundquist number. That's the critical point. Beyond that critical point of this, where you have secondary plasmoid instability, that is now taking along you on this path. So then within the Sweetparker model itself, even without invoking Hall currents or pressure gradients, you have the recipe for getting fast reconnection that is not falling off like 1/s to the half, but is actually reaching a steady value through the pathway of these secondary instabilities. We can give some very simple scaling arguments that actually make sense of this simple picture. Imagine that you have a critical Lundquist number over which the instability is triggered, and then you make the following conjecture, that the instability is triggered, you get a thinner current sheet, but make the conjecture that this current sheet would have the critical length and then go unstable again. But since the length is decreasing, the Lundquist number is dropping, eventually rises as the current layer stretches. And if you think of every one of the steps in the hierarchy as Sweetparker-like, you can demonstrate very quickly in a few lines that the reconnection rate would scale like V alpha n divided by square root of SC, not S. S would be the Sweetparker scaling. SC is that critical Lundquist number over which the sheet goes unstable. That's 10,000, okay? That's a fixed number. That's 0.01 VA. And the number of plasmoids can be humongous. They scale like S over SC, and we've actually checked this out numerically in our code. This is the nonlinear plasmoid rate, this is the linear plasmoid rate at sufficiently high values of S. You're going to be in this regime. Now, is the reconnection rate large enough? Well, it's 100th of a VA that can be adequate in the many coronal contexts, especially in the chromosphere and some other places, but not always. Because if you look at events, reconnection rates typically vary from 1,000th of a VA to about 0.1 VA. You can't make this go to 0.1. So a natural question is, when you're getting these current sheets thinned down, well, won't Hall terms matter again? Yes. They come in, and what do they do for you? They in fact give you an interesting phase diagram for reconnection that we never had before. In the beginning, we had two types of reconnection, Sweetparker reconnection and Hall reconnection. But now these plasmoid instabilities come, and they give you new possibilities, whereby you could have plasmoid-dominated reconnection that is more Sweetparker-like, or Hall reconnection which is dominated by plasmoids. Well, what happens if you turn on the Hall currents in these movies is that you actually find that the reconnection rate can go up to 0.1 VA. But that's not the only possible scenario. I'm giving you three possible runs here. This is Sweetparker, this is Hall-like, and these are sort of the intermediate plasmoid-dominated regimes that are kind of interesting. What happens on the extreme limit, the very Hall regime, you're back to your X points. All the plasmoids are expelled, the system gets back to a pure X point, you get this 0.1 type VA reconnection rate, and you're back to the old picture. But it is not the only possible picture. Now, due to the presence of secondary instabilities, you can have other possibilities. And before I show you that possibility in the Hall MHT model, I want to show you what came out of Dalton's PIC studies. See, PIC studies, which employ fully kinetic equations, and Hall models, had an interesting divergence. The divergence is that in particle and cell studies, same initial conditions, what happens is, you see this plasmoid instability is happening. This is particle and cell simulation with some amount of collisions. You see this extension, you see the plasmoid instability. But this process of extension goes on in particle and cell models, much in the same way as it happens in resistive MHT, except that it happens at a higher reconnection rate. Whereas in purely Hall models, we were tending to have this collapse to the X point, as pointed out by Kassak and Shepard in their paper. What Yimin Huang and I found with Brian Sullivan was something different. We found, in fact, in the largest 2D Hall simulations done of late, that the unique Hall state in the presence of the plasmoid instability is not just a pure X point, but it could also go through a metastable state where the system would alternate between a pure X point that can then again extend itself, form plasmoid-like structures, and show some qualitative features similar to PIC models. So the statement that Hall models always give you a unique X-point time structure is not necessarily true. In fact, new experiments designed by the Princeton Plasma Physics Laboratory called the MRXU or the MRX upgrade are planning to explore this plasmoid-dominated regime, and there's a lot to do here still. And I just want to show you very quickly that these have enormous consequences. Particle acceleration is a huge problem in an open problem. And roughly stated, it is this. If you look at solar flares, for example, and this has been made very clear by RESI observations, what you find is that when there are flares, you energize an enormous number of electrons to very high energies. If you just relied on a pure X point, or a Y point, it is unlikely, you will get large energies, no question, but it's unlikely that you will actually generate the large numbers. It's called the numbers problem. So what people are looking for are coherent structures that are more space-filling, that can actually produce major acceleration. Islands, seed, are a way to do that. And this is a picture from the Earth's magnetotail. I'm going back and forth between the magnetotail and the corona because I firmly believe that the physics that we are studying is common to both. It just is that the magnetotail gives us a great opportunity to learn about islands in situ. And so this is a paper done by Li Jian Chen in my group. And she is a clever detective who goes about trying to diagnose magnetic islands by looking at magnetic field line traces of the so-called BZ field. This is her coordinate system. And if you should cross multi-satellite configuration like cluster, should cross the separatrix of an island, the BZ field would look like this. And what Li Jian does is to use that signature to diagnose how many islands that she's crossing. So she feels that she's crossing like 10 islands in 10 minutes. And not only that, she finds that there's density peaking at the center of the island, the so-called O points of the island, not the X points. The classical configurations of reconnection emphasize X points, but she's finding density peaking at the O points. And if you look at the energetic channels, you find that more energy is created, more energetic particles are created at the center of the islands than at the X points. Now, this is a very intriguing finding, which is telling you that islands, these macroscopic structures, can play a very important role in particle acceleration. We don't understand all of this yet. The Drake has an interesting theory on Fermi acceleration, which I do not think quite works in 3 dimension. But nonetheless, he's right in emphasizing that islands can play a very important role in particle acceleration problems. And this has been seen in heliospheric current sheets. You see a sequence of observations where people, even though it's under-resolved, they're trying to get at these plasmoid structures. And the reason why they have a little bit more luck, because some of these plasmoids are huge. They're big in size, and they're much larger than the current layer itself from which they emerged. This can sometimes bring them within the realm of spatial observations. In my group, Ligia Guo has been trying to do a statistical study. She is one of your compatriots, so you should talk to her. Eyeballing some of these large-scale plasmoid structures, calculating how they're distributed, and trying to come to a more precise description in comparison with theory to figure out whether in the post-coronal mass ejected heliospheric current sheets, you have the dominance of this sort of plasmoid structures. This subject is becoming of greater and greater interest. It ties in heliospheric current sheets to what are regarded as tadpoles or superarcade downflows in the corona. And I've organized, in fact, a session in SHINE this year, in which I hope some of you will be participating, to talk about these sorts of phenomena as they pertain to the sun. Okay? Summary. Essentially giving you 2 mechanisms, all right, for slow growth and fast onset. In systems of moderate size, Hall MHT effects work rather well. You saw that. Transition from Sweetparker to X-point line. Larger systems, and we have done systems up to 10,000 ion skin depths long, you have a different route. So the plasmoid instability, which already in the resistive limit gives you faster connection. But then if you put in Hall, you get even faster. Okay? I think I can safely say and claim this, that in the last 10 years, we have solved the fast onset problem. You can get to 0.1 VA through a multitude of ways, and we know how to do it. I know this is a statement of great confidence, but I think we can collectively claim as a community we have solved the fast reconnection problem. That does not mean we have solved everything at all. We don't understand much about particle acceleration at all. We don't understand much about substorms yet, but I hope we will. We don't yet understand how reconnection manifests itself in flares and CMEs. I also want to tell you that large systems have surprises. They don't always produce a single X point. Yeah, we can get to 0.1 VA. In an intermediate regime, the system can alternate between a single X point state and a state with multiple X points. In geometry such as the tokamak or the Earth's magnetotail, ideal instabilities can play a very important role in addition to reconnection. And the 3D evolution of such systems I haven't even touched on, that John Derrelli touched on in his talk. That would be definitely a subject you want to get into, is wide open systems which actually have null points in them, or even not. How do you describe reconnection in such systems is an open area. Finally, I was in France for sabbatical, and so there is this beautiful picture of Sisyphus, and I often think of Sisyphus as, magnetic reconnection is the Sisyphus of the universe. It works tirelessly. And Camus, the novelist, more or less the philosopher, once said that he thought Sisyphus was pretty happy pushing up the stone and having it roll down all the way. This is exactly what happens in magnetic reconnection. It is the Sisyphus of the universe. It works tirelessly, pushes stones up, things to relax back, pushes it up again, goes up, on and on you go. And Camus claims the Sisyphus is rather happy. Thank you very much. Questions, comments? I went a little over time than I meant to. Digressions and all, but please. Yes?
I have a question about
So you're asking me a very good question, and there are gaps there. Sure. I'm being prompted now to do this for the nth time, and I forget all the time. The question is, can you distinguish a Helmut streamer from an extended current sheet? So Helmut streamers there are some people in the audience who know more about this than I do, but Helmut streamers have certain characteristics of extended current sheets. But whether they truly represent topologies in which the field lines are pointing in opposite directions remains to be settled. For example, in the Earth's magnetotail, which is not a Helmut streamer, if you take a dipole field and you thin it out, it looks like it has that character, except for the fact that the dipole has a little rounding off, right? As long as that rounding off is there, the field lines are not really pointing exactly in the opposite directions, because field lines are going like this and coming back like that, right? It's all pointing in the same direction. So I claim topologically, there's a huge difference between having a little BZ field that bends down your thing and one where the field lines are strictly reversed. Helmut streamers might have such complicating features of microstructures within, where the overlap region between field lines pointing in opposite directions may be confined to certain regions, but then the other regions where that is not so. Dana, would you like to add to that? Okay. Okay. More questions? Yes.
Regarding the substar ones that you showed, like results on resistive MHT and all MHT, which managed to resolve 2 out of the 3 time scales, how do kinetic codes cope with it today?
You know, that's a real. I haven't yet seen a kinetic simulation which will take the place of our Hall simulation, which actually puts in the Earth's dipole field and all of this. Pritchett has done work. The problem, as you know, since you know about particle and cell simulations, is loading particles. MHT gives you so many choices of equilibria, whereas in particle and cell codes, you have to have the extra challenge of loading particle distribution functions that are compatible with a macroscopic equilibrium. Pritchett has done work in this area by actually starting with Harris sheets, which are exact solutions of the Vlasov equation that I referred to, and then relaxing them by putting them dipole fields. But I have not seen Pritchett ever do this run. And Doughton, who is able to do this because he has at his command a very good high-performance code and the computers, has not done this problem. My speculation is that if you do this, you will see similar things. But it will be worthwhile to do. You might find some new things that were not found in Hall MHT, let alone the problem of doing it in 3D, which for a mass ratio of about 1/25 or maybe 100, you could do in 3D with present-day computing capability. Undoubtedly, LaPanta's codes, which you know well, are able to do that.
In the 2 simulations that you showed initially for the Hall MHT, there was an asymmetry in the flow.
Yes.
What is that?
That's in fact an outcome of the initial condition. And it doesn't, did you say asymmetry or asymmetry?
Symmetry.
There is symmetry, right?
It's not symmetrical, right?
Oh, if you do this sort of symmetry, qualified answers slowly. If you have no guide field in the problem, there is no magnetic field out of the plane of the paper, then there would be symmetry, both left, right, up, down. But if you put in a guide field in the problem, you break that symmetry. And one of the simulation results I might have shown you might have a guide field in it. Nonetheless, the overall picture that I was just telling you about is still correct. More questions? Yes, Nicholas.
Amitava, this question comes up with when you talk about some of the situations that we look at. The input equations to LFM and I think XRS are all ideal MHT.
Right.
Do I not?
Absolutely. Thank you for asking that question, because some of the very tools of research that Nick and Masha are using with you are global models, and these are very powerful tools. Despite all my cautionary words about global models, there's no denying that they have been extremely... Right. I don't want to do that too much because global models have taught us a lot. So what Nick is pointing out is that they often have what is called ideal MHT equations, but they show reconnection, right? Why? It's partially numerical, right? When it is not put in by hand, eta j, why are field lines reconnecting? It tells you numerical inaccuracies. So if you finite difference the equations, and you do the simplest finite difference scheme, you can show that you generate essentially a numerical resistivity term that has the appearance of physical resistivity that connects field lines. And many of those codes, when they're run with grid points, it's very hard to get them to have low resistivity. So I don't want to give MHT too bad a rap. I've repeated time and again that MHT is very good at large scales. Even when you understand the reconnection problem more precisely, you know where an MHT is going wrong. It's going wrong in those cases where, in fact, you get a narrow current layers. So what he's referring to is the fact that global codes often have uncontrolled numerical resistivity. So take their lessons seriously when they're talking about large-scale dynamics. Be very watchful when you get to the small scales. A lot of codes have trouble there. Masha? I agree with that comment. I agree with that comment.
So there is a way actually to work with MHD as soon as we make some transfer precision. That makes sense?
Yeah. Phil?
Very intrigued by the fact that you critical nucleus number coming from the different physical regimes. I wonder what that means for hypothetically an observation that shows wires that can have 10 to the 32 ohms, and then other ones that can have 10 to 5 ohms.
Yeah.
I would have thought that a critical nucleus number would kind of wouldn't allow you to build up enough free energy to allow this scale of range scale of flares to occur. So I just wonder if you have a thought about that.
Yeah, I've thought about this a lot. So, first of all, the plasmoid instability is a secondary instability. So it takes for a little while for the current sheet to build up. In the magnetotail, the thinning down process is what I call topological preparation time or whatever it is. It takes about 30 to 45 minutes. And these codes are able to reproduce that before they go unstable. Is that long enough for flares to store enough energy? Maybe, maybe not. I'm not sure. But let me just say a couple of things that I haven't covered in this talk, which is that just because you get thin current sheet doesn't always mean you get fast reconnection. Because there are mitigating factors. For example, in the laboratory plasmas, this has been well diagnosed, that you have what are called diamagnetic flows, sheared flows driven by pressure gradients in system, which have a tendency to stabilize fast reconnection. So you can get thin current sheets, but then if omega star effects, which are proportional to diamagnetic flows, come in, they can stabilize you nonlinearly. And this may be part of the reason why you get convection bays in Earth's magnetotail, not quantified as such yet, where you see a thin current sheet sit around for a long time, but the thing doesn't produce a substron. Or if you go to the dayside magnetopause, where you have opposite pointing field lines, you're not always seeing fast reconnection. And it's been speculated that other mitigating effects, which are harder to quantify, are preventing this from going unstable. So I would like to therefore say that the critical Lundquist number by itself should not be taken with a little bit of a grain of salt as setting sort of an absolute threshold, because we don't know other pieces of physics that may be working to stabilize the system when the simple considerations such as what I am talking about here predict instability. If there are no more questions, I'm around all week. Let's break for coffee, and I thank you all very much for your attention.